Let's continue the academic section. The second talk is by SitenderKashyap, PDF from IMSc.
Good afternoon, everyone. It's my great pleasure to be able to give a talk on such an important occasion in IMSc's history. And I thank Professor Sayantan for asking me to give a talk. And this talk is basically inspired from discussions with Professor Amritanshu and Sayantan, and is based on a work that I completed with one of my collaborators, Mrityunjay Varma. So the topic is essentially what you read in the title: how physicists can arrive at new mathematical identities using, the answer is, I'll provide the answer by giving an example from string theory. There are various ways. This will be one particular way. So in case I miss reaching the last slide, this is the answer. So there are three blobs here. The top one is for a particular, suppose you have a theory and there are certain physical quantities there. Okay, so on the top blob you can see that there are certain physical quantities in a physical theory. Now assume that that theory has not just one formulation but various formulations. Let's say formulation A and formulation B. Now consider a particular quantity, physical quantity, which you calculate using formulation A, which we call in the lower blob, square blob, as A of some collection of functions theta I. Similarly, you calculate the same physical quantity using the formulation B, and the result that you will get, let's call it B of theta of j. Incidentally, this theta is also is a symbol for the Jacobi functions, and this is what we will see in the last slide. So, okay. Now, the crucial assumption is that the formulations are equivalent, and hence what we must find is that A of theta I is equal to B of theta I. Now the thing is, on the left hand side, the theory, the formulation may rearrange the theta i's in a very specific way. Let's say products and linear combination of these functions. On the right hand side, we do not know how it will do. So at the end, if we demand this, we may get some non-trivial identities. Like for instance, on the left hand side, we will have something, and other side something. So it will, now, okay, so this is how it will go about. And my job in the rest of the talk is to tell you about all those three blobs and the formulations. And that we will do in string theory. Okay, so here is the plan, introduction to string theory, very basic. And then the two formulations that I will be using, those will form the A and B that I talked about. Then the physical quantity of import that we will use is the mass renormalization, and that too at a particular level, one loop. We'll see what it is. So, and then we will compare these two answers, and then comparison will lead to certain identity. And we'll mention what happens later. Okay, so string theory. Now, string theory, what is string theory? String theory is an attempts to describe all fundamental particles and interactions among them in a single framework. Now, it's a really paradigm shift, because instead of considering fundamental particles as point-like, we consider them as string-like. Okay? So this is a major fundamental shift. It's a hypothesis for the time being. In any case, let's recall what we read in high school physics. We think of fundamental particles as made out of, they are point-like, but we know that, for instance, if you take molecules, it has substructure, it is made up of atoms. Then atoms are made up of, they are also not point-like. They have substructure, electrons revolving around nucleus. Electron, so far as we know, it's kind of fundamental. That is, it cannot be broken further, but the nucleus can be in protons and neutrons. We also know that further proton is composed of quarks and gluons bind them, similarly for the neutrons. Now, so this is what is known physics. We aim to go beyond that. Where does this hierarchy, like we keep on breaking apart particles and go even more fundamental. String theory gives a proposal that eventually we will end up with one-dimensional object called strings. Okay, so let's go next. So what does, so let's see what is the basic difference between points and strings. So imagine that this, on the vertical axis, we have time flowing along, and consider point particle, it's a mathematical point, string which can be open or it can be closed. Let's evolve these three. So what we'll see is that particles, they will trace lines, and strings, they will trace sheets. So these are called wall lines, these are called wall sheets. So in the above, there is no interaction and we have just point particles and strings. However, non-trivial physics is all about interactions. So let's see in pictures how it happens. Yeah, so there are various physical quantities of relevance in physics. One such quantity is scattering. And what is scattering? Scattering is a process in which objects come together from far afar, they interact, and then they go away, far away. So here is a diagram in the point particle case and strings. Imagine at this time, there are two particles, they become one, there is some virtual particle created, single particle, it remains single, and then it again pair produces and gives another part, two set of particles. Similarly for strings. But this is not the end of the story. What happens is that particles can split or join many times over. And if they have, and these are called something called quantum loop corrections. So this is what, so now let's take this diagram. Here we have two strings to begin with at this time. Let's go move in time. Here we have still two strings. Here we see that they have joined to form one string. Then they split and form two strings. Again they join and form one string and two string, one string, and then finally they separate. So this is the process of scattering as described in string theory. Now, what is the objective? The objective is to take this set of initial strings, I mean how they are vibrating, what is their initial state, given that, and given a set of final states. What is the probability of this configuration of strings to go to this configuration of strings? There can be more than two strings, okay? So that's all. Now we'll put it in mathematical language. So those were all diagrams. Now let's see, those diagrams actually have precise mathematical expressions. Now for instance, scattering amplitudes are given in terms of, in terms of what is called Polyakov prescription. To say in very brief words, Polyakov prescription gives us a weighted sum over compact topologies, okay? What this means is the following expression. Here A is something called scattering amplitude. It depends on the momenta of the external strings k1 to kn. Okay, so this is the left hand side. On the right hand side, it is sum over compact topologies. What that means is that we consider, in case of let's say 4 external strings, topologies with 0 handle, 1 handle, 2 handle. Handle means this guy, you have just 2 handles in which you can hold. Okay, so this thing is now clear what it means. Let's go to the weighted part. So this is the exponential and exponential of something. So this guy provides weight for each of these topologies, okay? So here we see that S of phi is something which is called action of fields that live on the on these manifolds, okay? And chi is the Euler character, forget about it for the time being. And then there is another part which is here. So in this guy, let's see, from top diagram, we are going to the bottom diagram. These looks very nice mathematical objects. Here what is happening is that these external strings, we can go to a set of coordinates and we can rescale the matrix in such a way that these just become point, the external strings, okay? So in that way, we have the full amplitude is given in terms of sum of all these different topologies, okay? And here k sigma is the coordinate on the world tube. So this is all about the Polyakov prescription. Now the lowest order term, when we have h equal to 0, this we shall call classical. On top of this, there will be these contributions. These will be suppressed, and yeah, so that's all. So other will be like, one loop will be, for example, this. Okay, so now, I described the theory, the top part. Now let's look at the formulations A and B. In this case, in the case of string theory, there are not just one formula or two formulations, there are in fact 3. Oops. Yeah, so there are 3 standard formulations. The oldest one called Raman-Nebuchois, the next one called Green-Schwarz, and the final one called Pure Spinner. This is where I work, and these are the name of the people who build this. and the person who essentially wrote the action for this is Nathan Berkowitz. Now, all these formalisms use different ingredients to describe the dynamics of the fundamental string. The fundamental variables in these formulations transform under different representations of the super Poincare group. Suppose we are in flat space-time, so the group is this. These the fundamental variables will transform in different representations, as I will mention. So in what follows, we shall use this guy, the RNS formalism, and this guy, the pure spinor formalism. Okay, so this is the thing. Here we have the formalism, RNS, and pure spinor. Now the fields, as I said, when I showed the Polyakov action, there was this phi. Phi represents collectively all the fields that live on that manifold. Fields are any variables which take value throughout the manifold. Okay, so these can be divided into two sectors: matter sector and ghost sector. So from here, basically, for example, this XM, which appears in both pure spinor and RNS, is a space-time vector. That is, it transforms in the fundamental representation. And then we have which is a worldsheet scalar, and it's a Grassmann even field. Grassmann even means if you exchange them, there is no sign change. Grassmann odd means if you exchange them, there is a sign change. Okay, then we have this other variable called psi m. This is a space-time vector, but it's a worldsheet Majorana spinor and is a Grassmann odd field. So just from this, we can see even the ghost sector is different. Here, BC are the standard BC ghosts that appear in bosonic strings, and there is something called beta gamma system. Okay, let's not go into the detail of these. The whole point from here is that these formulations are written in terms of different mathematical objects. Okay, yeah. So I hope that the above list is sufficient to see that these formalisms cannot be trivially mapped to each other. In fact, a rigorous mathematical proof is still not available. Okay, that these are essentially mathematically equivalent. Okay, but they have been shown to be equivalent by many tests. So pure spinor was introduced in year 2000. So 21.5 years of its existence. There has been nothing against that these are not equivalent. Okay. Okay. So now, what is the advantage of having multiple formalisms? First advantage is that if a feature is difficult to describe in a particular theory, in a particular formalism, it can become simpler in other formalism. For instance, the pure spinor formalism, which is just 21 years old, and RNS, which is around maybe 40 years old. So that has been able to calculate all the string amplitudes computed in RNS formalism, and in fact, it has superseded RNS formalism in this particular aspect. There are certain aspects where RNS is still the preferred choice. Now, second thing is the robustness of underlying physics. This means no matter what language, that is, for instance, what kind of mathematics you use, one lands up with same physics. So this kind of gives you confidence, oh, this structure definitely may have something deeper inside it. Now, final point is this, that it can give us the possibility of new mathematical relations, which is goal of this talk, but not of physics in general. So let's move. Now, let's come back to the physical quantity that we wanted to compare, and that physical quantity is called mass. We know all mass. We all know mass. So let's see. So quantum effects do and will change classical values unless some symmetry protects them. Loop contain this information by how much it is changing. Remember, I said by classical I mean zero handles. So this guy is classical. This is first quantum correction. This is second quantum correction, and so on and so forth. Now, as I said, any quantity will change under quantum corrections. So same is true for mass of a string. Okay, string has mass, and it is a physical quantity which will undergo quantum corrections. So now the information, this effect is physical and will not depend on what formalism we use, RNS or pure spinor or even Green-Schwarz. Now, 2-point string amplitude contain the information about mass. In mathematical language, this means it is the residue of the pole of the momentum squared in the momentum space. So let's, this 2-point function, this is essentially sphere, 2 strings here, 2 strings here, 0 loop, 1 loop, 2 loop. So we need to calculate this. I gave you the starting expression which can be used for these. This guy will have certain expression and we can put it there and do the computation. Now, we can calculate the 1 loop contribution, that is this, to get the quantum correction to the mass. And in our particular case, we took a massive string state and then computed this guy, okay? So, yeah. So now using the RNS formalism, one finds, in fact, Ashok Sen did the work in 2013, and this is the answer that he finds, okay? Now the feature, I'll just mention a few features about this. This guy is the modular parameter, this guy is the position of the string on the world sheet. And so conveniently I have divided these expression into 3 pieces, 3 curly brackets, curly bracket 1, curly bracket 2, which ends up all the way here, and curly bracket 3, okay? Now using the pure spinor formalism, this is my collaborator Mrityunjay Verma, we'll put it out maybe in a couple of days. So this is the answer that we find. Now once again, in order to compare with this, we have divided this into 3 curly brackets. The first curly bracket is exactly same, second is exactly same. Of course, here you see theta 1, 1, here you see theta 1, but this is because people use different notation for Jacobi theta function. We choose to just use one index, they use, Ashok used 1, 1, etc. So, yeah, now where is the difference lying? The difference is here, the blue thing here, you see an eta to the 8 here, okay? Now, what does that mean? If these are equal, what does that mean? That essentially means that this blue line, this must be a constant, okay? So, comparing these two results, we must conclude that the terms in blue must be a non-zero constant. And hence, we arrive at, yeah, so we arrive at this guy, this is -4. When we set it equal to some constant, it will become theta 1, 1 raised to 4. So, this is what we get, where this Kronecker delta means something, okay? Let's not go into the details of it. But now, this was a sample calculation, and the above identity is already known in mathematical literature, okay? These are called Riemann identities. Sen used these to simplify his answer to what we got in the pure spinor formalism, which means his raw answer was in this form. He used Riemann theta identities to come to this form. Now, our formalism, or the formalism in which we work, directly gives us this answer, okay? So, yeah, so now as I said, so this particular Riemann identity is already known. Now calculating, so this, remember, this is just 2-point function on torus, but there is no limit to what you can calculate. You can calculate 4-point1 loop, 6-point n loop, n-point1 loop, let's say, or you can go higher in genus, 2 loops, and so on and so forth. So what will happen is, if you use the RNS formalism, you will get sum over this is something called spin structures. So you will get sum over spin structures, but somehow, magically, the pure spinor formalism already knows how to sum over spin structures. So what you can do is, suppose the Riemann identities are not known. So using RNS, you will be just stuck here. You do not know how to proceed further. You cannot simplify the answer further. But pure spin, if you use pure spinor, you will directly arrive at the answer, even for those complicated amplitudes, okay? Yeah, so this is my final 2 points. So calculating higher point amplitudes at 1 loop and higher loops, we shall potentially arrive, notice the word arrive at some non-trivial identities unknown in mathematics literature. But the point is, this is not a mathematical proof. It is like inspiration that, okay, go look at this relation, maybe it's mathematical identity. Of course, the point is, we shall leave it to our mathematics friends to prove them mathematically and help us advance further. Why? Because that will prove that the formulations are really equivalent, if you can really prove it. As I said, there is no proof for equivalence of these two formalism, mathematical equivalence. So all we rely is we calculate certain quantities and match. And if we calculate another, let's say we have calculated n such quantities and n plus 1th we calculate, if they match, then we have more confidence in our theory, okay? So far, let's say 22 years, this has been the story. So yeah, maybe our mathematician friends, if we arrive at some identities which we cannot prove, they can help us prove. With this, I'd like to end. Thank you.
Thank you, Sitendra.